Welcome to Ultimate Sleep Doctor. Tonight, we'll be exploring a concept that whispers of the universe's ultimate fate. Entropy, the tendency of systems to move towards disorder, is a fundamental law of physics. It's a notion that suggests everything eventually will spread out, lose its form, and diminish. The idea of heat death paints a picture of a universe, incredibly vast and ancient, cooling towards a state of absolute equilibrium. There's a quiet beauty in this immense scale, isn't there? A reminder that even the most complex things are ultimately part of a continuous, unfolding process. Let your thoughts drift like clouds across a silent sky. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe, let your worries soften. Let's begin. Let's consider the universe not as a grand, orchestrated symphony, but as a colossal collection of tiny, restless particles, atoms and molecules, constantly jostling and interacting. These particles, governed by the fundamental laws of physics, behave according to probabilities. It's not that they intend to arrange themselves in intricate patterns. Rather, there are simply far more ways for them to be disordered than there are ways for them to be perfectly organized. This is the core of what we call the second law of thermodynamics. The second law states, in essence, that the total entropy of an isolated system can only increase over time or remain constant in ideal cases. Entropy, you see, is a measure of disorder, randomness, or, more precisely, the number of possible microscopic arrangements corresponding to a given macroscopic state. A neatly stacked pile of blocks has low entropy. It represents a very specific arrangement. But if you shake that pile, the blocks will scatter across the floor, a far more probable state with vastly more possible arrangements. Now, let's delve a little deeper into this with statistical mechanics. This branch of physics uses probability to describe the behavior of large collections of particles. Instead of tracking every single atom's movement, we consider the statistical likelihood of different arrangements. Imagine a gas confined to one side of a container. Because of the random motion of the gas molecules, they're constantly colliding and bouncing around. There's a much higher probability that they'll spread out to fill the entire container. The natural tendency is towards this dispersal. It's not that some force is pushing the gas to spread out. It's simply that the disordered state is statistically much more likely. Think of shuffling a deck of cards. After just a few shuffles, the cards become thoroughly mixed, a highly disordered arrangement. It's extraordinarily unlikely, though not impossible, that you'd be able to perfectly rearrange them back into their original order. This principle extends to everything in the universe. Chemical reactions tend to proceed in a direction that increases entropy. Heat flows from hotter objects to colder objects, dispersing energy and increasing disorder. Even the formation of complex structures, like a snowflake, requires an input of energy that ultimately increases the overall entropy of the system and its surroundings. Furthermore, the arrow of time, that feeling that time moves in one direction, is intimately linked to this increasing entropy. We experience time moving forward because the universe is constantly becoming more disordered. The reverse process, a spontaneous decrease in entropy, would require an incredibly improbable event and one we never observe. It's as if the universe has built-in bias towards disorder. This unidirectional increase in entropy isn't just a quirk of our current understanding. It's a fundamental property of the universe, dictated by the statistical behavior of its constituent particles. It sets the stage for some profound questions about the ultimate fate of everything, a journey we'll explore in the coming parts. Let's delve now into a truly bizarre corner of the universe: black holes and their surprising connection to the concept of entropy. For a long time, black holes were simply considered cosmic vacuum cleaners, objects so dense that nothing, not even light, could escape their gravitational pull. But physicists like Stephen Hawking began to challenge this simplistic view, realizing that black holes weren't entirely empty. They possessed a hidden thermal energy and, consequently, a temperature. Hawking's initial calculations, developed in the mid-1970s, revealed a remarkable phenomenon. Black holes aren't completely black. Instead, they emit a faint glow, a stream of particles, now known as Hawking radiation. This radiation arises from a quantum mechanical effect near the event horizon, the boundary beyond which escape is impossible. Quantum mechanics tells us that empty space isn't truly empty. It's a bubbling soup of virtual particles that pop in and out of existence for fleeting moments. Near the intense gravity of a black hole, these virtual particles can briefly form, one falling into the black hole and the other escaping. This process creates a continuous flow of energy and therefore a temperature for the black hole. The smaller the black hole, the hotter it is, and the more vigorously it radiates. It's a fundamental link between gravity, thermodynamics, and quantum mechanics. A black hole's temperature is inversely proportional to its mass. A tiny black hole would be scorching hot, while a supermassive black hole would be chillingly cold. However, this seemingly straightforward picture quickly ran into a profound puzzle: information. What happens to the matter that falls into a black hole? According to classical physics, it's crushed into a singularity at the center, and all traces of its existence are lost. But information, in the context of physics, refers to the precise arrangement of matter and energy, the complete description of a system. The conservation of information is a cornerstone of quantum mechanics. Information cannot be truly destroyed. This contradiction became known as the information paradox. If a black hole evaporates entirely through Hawking radiation, carrying away energy, but not returning that energy to the universe in a way that precisely reconstructs the original state of the infalling matter, then information is genuinely lost. This implies a fundamental breakdown in our understanding of either quantum mechanics or general relativity, or perhaps both. Numerous theoretical solutions have been proposed, including the idea that information is somehow imprinted on the outgoing Hawking radiation itself. Some physicists speculate that the information might be stored on the event horizon, encoded in a complex pattern. Others propose that black holes eventually bounce, leading to a new universe containing the information that was previously lost. The information paradox remains one of the most actively researched problems in theoretical physics, constantly pushing the boundaries of our understanding of the cosmos. Let's consider a truly bizarre thought experiment, one that challenges our fundamental assumptions about the universe. It begins with the work of Ludwig Boltzmann, a brilliant 19th century physicist who painstakingly described the behavior of gases and the relentless march of entropy. Boltzmann argued that, given enough time and a sufficiently large collection of particles, anything that is even remotely possible will eventually happen. It's a consequence of sheer probability. Now, imagine a vast, empty region of space, a region so large that it contains an almost unimaginable number of particles, perhaps trillions upon trillions. These particles are arranged in a completely disordered state, a state of maximum entropy. Now consider a single particle. Let's say this particle, purely by chance, spontaneously organizes itself into a complex structure, a brain with memories, thoughts, and the capacity to experience the universe. It's a fully formed, conscious entity, existing entirely within this otherwise random, chaotic sea of particles. This is the Boltzmann brain. It's not a deliberate creation. It's a consequence of the statistical possibilities arising from an incredibly large number of particles. The probability of this occurring, even given an enormous number of particles, is astonishingly small. It's like winning the lottery every single day for billions of years. The odds are so staggeringly against it that it seems utterly impossible. Yet, Boltzmann argued, if the universe is truly vast and has existed for an incredibly long time, far longer than the current age of our observable universe, then, simply by chance, Boltzmann brains could, and perhaps have, spontaneously arisen. This unsettling thought has led to the development of the anthropic principle. The simplest form of the principle states that we observe the universe to be the way it is because, if it were any different, we wouldn't be here to observe it. In other words, the fundamental constants of nature, the strength of gravity, the charge of an electron, the values of fundamental physical constants, are precisely what they are because if they were different, the conditions necessary for the emergence of life, and therefore our existence, would not have existed. However, a deeper, more disconcerting interpretation suggests that the anthropic principle isn't just a consequence of our own existence. It suggests that the universe must be compatible with the existence of observers like us. If the universe were governed by physical laws that prevented the formation of complex structures, life, and consciousness, then we simply wouldn't be around to ask the question. The universe, therefore, is self-selecting. It favors arrangements that allow for observers. The prevalence of Boltzmann brains raises serious questions about the validity of this interpretation. If Boltzmann brains can, and potentially do, arise spontaneously, then our own consciousness might not be the result of some grand cosmic design, but rather a mere statistical fluke, a random occurrence in an overwhelmingly chaotic universe. It challenges our understanding of our place within the cosmos and forces us to confront the uncomfortable possibility that our perceptions of reality are profoundly unreliable. The universe, it seems, may be far stranger and far less hospitable to conscious observers than we initially imagined. Let's consider entropy not just as a measure of heat dispersal, but as a gauge of how much organized structure exists within a system. It's a surprisingly insightful tool for understanding how things change and how much effort, in terms of energy, is required to maintain order. Take a simple chemical reaction, like mixing vinegar and baking soda. Initially, you have distinct substances, the clear vinegar and the white baking soda. The molecules are neatly arranged, separate. As they react, they form carbon dioxide gas, water, and sodium acetate. The bubbles rise, and the original substances disappear. This isn't simply about heat spreading out. It's about the creation of a far more disordered state. The molecules of carbon dioxide, water, and sodium acetate are now spread throughout the air, bouncing around randomly. The initial, organized reaction has demonstrably increased the overall entropy of the system. Now let's scale up. Consider a crystal like a perfect amethyst. It's a stunning example of order, with atoms arranged in a highly structured, repeating pattern. But even a crystal, given enough time and energy, will slowly degrade. Tiny imperfections will appear, and eventually it might break apart into a rubble of fragments. The act of breaking a crystal represents an undeniable increase in entropy. The system has transitioned from a state of remarkable organization to a chaotic distribution of its constituent elements. The energy invested in forming the crystal has been dissipated into a more disordered state. Moving to living organisms introduces a truly astonishing aspect of this principle. A human body, for example, is an unbelievably complex arrangement of molecules, meticulously orchestrated by countless chemical reactions. Our cells maintain incredible levels of order. DNA replication, protein synthesis, energy production, all demand a constant input of energy to combat the natural tendency toward disorder. We build and repair tissues, fight off infections, and maintain stable internal conditions, all acts that intrinsically increase entropy in our immediate surroundings, even as we locally reduce it. The sheer complexity of a biological organism, from a single bacterium to a towering redwood tree, acts as a temporary bulwark against the universal rise of entropy. However, every action, every metabolic process generates heat and waste products, further contributing to the overall disorder of the universe. It's like a constantly shifting sandcastle. You can build it high and elaborate, but eventually the waves will come and it will crumble. Ultimately, the concept of entropy isn't just about physical disorder, it's about the probability of states. A highly ordered system, like a precisely constructed machine, is an extraordinarily rare event. The universe, statistically, favors states of higher entropy. As energy is used to create and sustain order, be it in a chemical reaction, a living being, or a meticulously crafted structure, that energy is inevitably dispersed, contributing to the ever-increasing spread of disorder across all of space and time. It's a fundamental process, and one that dictates the ultimate fate of everything. The universe, as we understand it, isn't a static, unchanging place. It's actually growing, expanding outward, like a balloon being inflated. This expansion was first observed by Edwin Hubble in the late 1920s, and it's a truly remarkable discovery. Hubble meticulously studied the light from distant galaxies, noticing a crucial relationship. The further away a galaxy was, the faster it was receding from us. This isn't because galaxies are actively moving through space at high speeds. Rather, space itself is stretching, carrying the galaxies along with it. We describe this expansion with Hubble's law, which simply states that the recessional velocity of a galaxy is directly proportional to its distance. The further away it is, the greater its speed of separation. It's like dots painted on a rubber sheet that's being pulled apart. As the sheet expands, the dots move further away from each other, and the distance between them increases proportionally. This expansion isn't a gentle process, it's accelerating. This acceleration wasn't initially predicted, and its discovery in the late 1990s fundamentally changed our understanding of the universe. Two teams of astronomers, using observations of distant supernovae, found evidence that the expansion isn't just continuing, but it's speeding up. This acceleration is attributed to a mysterious force called dark energy. Dark energy makes up approximately 68% of the universe's total energy density, and its nature remains one of the biggest puzzles in modern cosmology. We don't truly know what it is, but its effect is clear. It's pushing the universe apart with ever-increasing force. It's as if the balloon isn't just inflating, but the rubber itself is becoming more elastic, resisting compression and actively pushing outwards. The ongoing expansion, driven by this dark energy, has profound implications for the future of the universe. As space expands, the density of matter and energy decreases. Galaxies, once gravitationally bound, will eventually move so far apart that they become effectively isolated. The light from these distant galaxies will be stretched to longer wavelengths, a phenomenon called redshift, until it's too faint to be detected. This expansion, combined with the relentless increase in entropy, paints a picture of a universe heading towards a state of maximum disorder. The second law of thermodynamics dictates that entropy, a measure of disorder, always increases in a closed system. In the expanding universe, this means that energy, originally concentrated in the Big Bang, is constantly being dispersed, becoming less and less available to do work. Eventually, the universe will reach a state known as heat death. In this heat death scenario, the temperature will approach absolute zero, and all available energy will be evenly distributed, leaving no gradients, no potential for further change, and no usable energy to exist. It's a remarkably cold and desolate future, a consequence of the continuous expansion and the ever-increasing entropy of the cosmos. The last vestiges of structure will dissolve, and the universe will be a vast, dark, and empty expanse, a testament to the inexorable march of disorder. The story of entropy, as we've discovered, is fundamentally about the universe's inexorable tendency towards disorder. But what if a clever little being could seemingly defy this rule, creating a pocket of order within a chaotic system? This is where the concept of Maxwell's demon enters the picture. James Clerk Maxwell, a brilliant 19th century physicist, proposed this thought experiment to explore the relationship between thermodynamics, information, and energy. Maxwell imagined a tiny chamber divided by a partition. On one side, a stream of gas molecules rushes in, randomly moving in all directions. On the other side, the molecules are still, equally distributed. Now, imagine a small demon, a being of pure information, sitting at the partition. The demon's task is simple. It observes each gas molecule as it approaches the barrier. If a molecule is moving to the right, the demon opens a door to let it pass. If it's moving to the left, the demon closes the door. The result, according to Maxwell's initial reasoning, would be a remarkable one. The fast-moving molecules would accumulate on one side of the chamber, while the slow-moving molecules would gather on the other. Effectively, the demon was sorting the gas molecules by speed, creating a region of lower entropy, a region of greater order, at the expense of increasing the entropy of the overall system. This seemed to suggest that information itself could be used to violate the second law of thermodynamics. However, as physicists began to scrutinize the thought experiment more deeply, crucial limitations emerged. The fundamental issue lies in the concept of observation itself. The demon isn't just passively watching. Its very act of observing, of measuring the speed of each molecule, requires the expenditure of energy. This energy, inevitably, must be dissipated into the chamber as heat, random molecular motion, increasing the entropy of the entire system. Consider the subtle interactions at the barrier. The demon needs a way to detect the molecule's speed, and this necessitates some kind of physical interaction, perhaps a tiny probe. This interaction, no matter how small, will always result in some energy being transferred, further disrupting the molecular arrangement. The demon can sort, but it cannot do so without creating disorder elsewhere. Furthermore, the demon's memory, the information it needs to keep track of which molecules have passed through, also contributes to entropy increase. Maintaining this information requires energy and creates correlations between the molecules, thus increasing the system's overall disorder. Ultimately, Maxwell's demon reveals a profound truth. Local reductions in entropy are impossible without a corresponding increase in entropy elsewhere. It's not that the demon is secretly defying the laws of physics. It's simply that the universe, in its relentless pursuit of equilibrium, will always find a way to balance the scales. The thought experiment serves as a crucial reminder that information, while powerful, is still bound by the fundamental constraints of thermodynamics, and that the universe's expansion continues to amplify the effect. The universe, in its relentless progression, isn't just expanding, it's steadily becoming more diffuse. This increase in disorder, this unwavering march of entropy, isn't just about the spreading of heat, though that's a significant part of it. It's a fundamental process that eventually begins to affect the very fabric of reality itself, touching even the most powerful forces that shape the cosmos. Let's consider the strong nuclear force, the glue holding atomic nuclei together. This force, responsible for the stability of atoms, is intimately linked to the energy contained within those nuclei. As entropy increases, the organized structure of nuclei, the tightly bound arrangement of protons and neutrons, becomes increasingly unstable. The energy needed to maintain that structure requires more and more energy to combat the outward push of disorder. Eventually, the energy available to overcome this destabilization diminishes. The nuclei begin to unravel, not in a dramatic explosion, but in a gradual, almost imperceptible disintegration. Protons and neutrons, no longer bound together, drift apart, forming a haze of fundamental particles. This process isn't immediate. It's a staggeringly slow transformation occurring over timescales far exceeding the current age of the universe. Similarly, the weak nuclear force, responsible for radioactive decay, similarly relies on a carefully balanced energy state within the nucleus. As entropy climbs, the delicate equilibrium required for processes like beta decay breaks down. Neutrons transform into protons, and vice versa, driven by the relentless tendency for systems to move towards maximum disorder. The electromagnetic force, while seemingly more resilient due to its interactions with charged particles, isn't immune. The precise ordering of electromagnetic fields, the intricate patterns of light and radiation, also tends towards a more chaotic state. The creation of coherent structures, like stars and galaxies, themselves represent localized attempts to resist entropy. These structures draw upon immense reserves of energy, but ultimately, their organized forms are susceptible to the universal tide. The energy required to maintain their complex configurations is ultimately dissipated, contributing to the overall increase in disorder. As these fundamental forces weaken, the universe transitions through a series of increasingly chaotic states. Initially, it's the breakdown of atomic structure, followed by the disruption of chemical bonds, and finally, the dissolution of all recognizable matter. It's a process where the universe loses its capacity to perform work, to create complex structures, to sustain anything resembling life or order. The very concepts of space and time, as we understand them, become increasingly blurred, stretched and distorted by the overwhelming influence of entropy. The end result isn't a sudden, catastrophic event, but a gradual fading, a slow dissolution into a state of unimaginable uniformity. It's a state where the distinction between energy and matter dissolves completely, where all forces have effectively ceased to function, and the universe exists solely as a vast, homogeneous soup of fundamental particles. A state often referred to as heat death, not because of temperature, but because all available energy has been dispersed and nothing can be utilized to create any further complexity or order. It's a quiet, almost serene end, born not of destruction, but of ultimate, irreversible disorder. The relentless march of entropy, as we've explored, seems to dictate a future of increasing disorder within the universe. However, the universe is far more nuanced than a simple, unidirectional flow towards chaos. Recent theoretical work, particularly within the realm of quantum mechanics, suggests a fascinating possibility: that quantum entanglement might play a far more significant role in shaping the overall trajectory of entropy. It's a concept that challenges our intuitive understanding of how information, and therefore order, is distributed across vast distances. Consider the peculiar behavior of entangled particles, two particles linked in such a way that their fates are intertwined, regardless of the distance separating them. If you measure the property of one particle, you instantly know the corresponding property of the other, a connection that appears to defy the limitations of the speed of light. This isn't about sending information faster than light. Instead, it's a correlation built into the very fabric of reality. Now, let's extend this idea to the cosmos. If the universe is fundamentally interconnected through quantum entanglement, then the distribution of energy and information is not solely governed by the second law of thermodynamics, which dictates that entropy increases in isolated systems. Instead, entanglement might introduce a form of quantum coherence across incredibly large scales. This coherence, a state of sustained order, could, in theory, resist the overall rise in entropy. Researchers are exploring the possibility that entangled systems, distributed throughout the universe, could create pockets of localized order. These pockets wouldn't violate the second law locally. They would still experience entropy increases, but their existence might effectively dilute the overall entropy of the universe. Think of it like spreading paint across a canvas. Initially, a single drop of vibrant color creates a stark contrast. But as the paint spreads, the color becomes less intense, and eventually it blends into a uniform hue. Perhaps the universe, through entanglement, is doing something similar. It's not eliminating entropy entirely, but rather distributing it in a way that allows for the temporary persistence of complex structures and correlations. It's a counterintuitive idea, but one supported by mathematical models suggesting that quantum correlations could provide a mechanism for preserving some degree of order against the relentlessly spreading tide of disorder. This doesn't necessarily offer a pathway to circumvent heat death. The sheer scale of the universe and the ultimate degradation of all physical systems still present a formidable challenge. However, it introduces a crucial element: the potential for quantum entanglement to act as a subtle, interwoven network, subtly influencing the rate and pattern of entropy increase. It suggests a far more complex and dynamic picture than a simple, predictable decline. It's a reminder that even in the face of profound cosmic changes, the universe continues to hold surprising and beautiful secrets. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. We've journeyed through the profound concept of entropy and the eventual heat death of the universe, a reminder of the beautiful, inevitable cycle of all things. Now, let your thoughts drift, calm and unhurried, carried by the quietest currents of your own being until sleep finds you. Good night.